talk about the next chapter in our textbook, which has to do with the conservation of mechanical energy. We kind of touched on this concept at the end of the last video that we had. So today we're going to do some example problems and kind of talk a little bit more about it. So you guys remember from last year that the sum of the kinetic and potential energies of an object is called the total mechanical energy of that object or system. Your book uses this connotation, so I think we should probably stick with it just so that you guys keep some consistency in your math and how you write your equations. So right now this equation works out really well for us whenever we're dealing with conservative forces. So these are things pretty much with no friction added into the equation. The next video we're going to talk about what happens when you have non-conservative forces acting on an object. So what do you do when there is friction? But right now, this equation will hold for most of our situations. So that means that the potential energy of our objects is going to be related to the gravitational potential energy of that object, and the kinetic energy is going to be related to, of course, how fast that object is moving. So we're going to do 3 different kinds of examples today. We're going to talk about slopes, pendulums, and a spring problem. So the slope problem that we're going to do is very similar to one you might have seen last year in pre-AP. So here's the first problem. Skier starts from rest at the top of a 60-meter high slope. What is her initial gravitational potential energy with respect to the level ground at the bottom? And then find out what speed she's going to arrive at the bottom at. And then a little bit extra part here on part C. At what point along the slope will she have a speed equal to half of the speed in B? Alright, so I'm going to change my ink color to be white here. So this skier's total mechanical energy is going to be equal to her kinetic plus her potential. When she's at the top of the slope, right, if this is our slope, this is 60 meters, her potential energy is equal to her mechanical energy because at the top of the slope she has no kinetic just yet. All of her energy is going to be potential. So for part A, her potential energy is going to be equal to her gravitational potential, which is mass times gravity times height. So that means that for part A, her potential is 36,000 joules. Alright, let's look at part B. Part B says, assuming that there's no friction, what would her speed be when she arrives at the bottom of the slope? So this is an exercise in energy transfer, right? At the top of the slope she has all potential, and then when she's at the bottom she has all kinetic. So that means that if there's no friction, she's not losing any energy along the way. So this 36,000 joules gets transferred into her kinetic energy. So let's compute that real fast. We get a velocity of about 34.6 or 35 meters per second. Yeah. So part C says, at what point along the slope will she have a speed equal to half of the speed in B? It's kind of tempting, and this might be something you would be wanting to say, is that she would be going half this fast when she's exactly halfway down the slope. But that's not the case in this scenario, and it's not because in the kinetic energy equation, our speed is squared. So that means that the height is related to the square of the velocity, it's not a direct proportion. So we're going to do 34.6 divided by 2, so that means that our velocity is 17.32 meters per second. So let's figure out what her kinetic energy has to be when she's going this fast. 17.32 squared. We're going to compute that. And we get that her kinetic energy is 9,000 joules. Alright, so if her kinetic energy is 9,000 joules, then that means the difference between what her potential energy was at the start and this kinetic energy is going to be her potential at that moment. So that means that her potential energy would be 27,000. So now that I figure out how much kinetic energy she has when she's going half of this speed, and I know how much potential energy she has when she's at this speed, I can do MGH and determine at what height along the slope or how high up off the ground she has to be when she's going this fast. And the height is 45 meters. All right, let's look at the next problem, which has to do with pendulums. I don't really think we talked much about pendulum and energy transfer in pre-AP. I'm sure you guys probably have seen a diagram like this at some point. A pendulum, as it swings back and forth, right, there's energy transfer that's taking place here. We have a situation where when it's pulled all the way out here to the side, let me just change my ink color so you guys can see this. When it's all the way out here to the side at point A, that's when it's at its maximum displacement from the equilibrium point. And in this photo, we're going to take the equilibrium point to be at point C. So when it's at that maximum displacement from equilibrium, that's when all of its energy is going to be stored in the potential. You release the pendulum and it swings from that height downward to this C point, right? So the energy transfer is that it's losing potential and gaining kinetic as it swings through this middle point. Now, since these are conservative forces and energy can't be created or destroyed, we're just going to assume that it's going to rise back to the same level at point D that it was at point A, and that means that you have a complete energy transfer taking place. So, as it goes from A to C, it's going to lose all of its potential and gain kinetic, right? And it's going to gain however much potential energy it had at point A. And then over here to point D will be exactly the same as point A. Now, point B, the part in the middle, if it has 2 joules of kinetic, that means that it has to have 0.4 joules of potential, because kinetic plus potential is going to give us our total mechanical energy. All right, so let's look at this a little bit. Okay, I have to go to my whiteboard now. That was a note for myself, so that I can remember to do that. All right, so let's draw this on here because it's better if I draw it a little bit larger. So, here's a vertical, and let's say here's a pendulum, and it has a string of length L. Oops, that's supposed to be an L. All right, the pendulum, the angle that this pendulum makes here with the vertical, this is our theta. All right. So when this pendulum swings through the vertical, it's going to follow this path like this, right? So it's important that you guys kind of see conceptually that when I pull this pendulum out to the side here, I'm raising it by a height here and here that I can just call H or Y or whatever I want to call it. So this height here becomes the height in our MGH expression for the potential, because this is how high I'm raising the pendulum from its equilibrium position down here at the bottom. So we can do a little bit of trig here to figure out what this distance has to be. Right? Here, when it's all stretched out to the side, this side of our triangle would be equal to our hypotenuse, which is L, cosine theta. That's going to be this bit right here. Now when I release the pendulum and it swings through the center point, this is our picture now, right? It came from over here and it swung this way, and now it's hanging down here in the middle. This is still L, right? The length of the string. It's not like the string got longer. So that means that the difference between the length of the string and L cosine theta So the length of the string here, the whole thing, and then this is L cosine theta. The difference between those two distances is going to be our h value. And if you can see that in pendulum problems, it makes everything so much easier. So let's talk about energy transfers and just what's happening so we can come up with some expressions here. So the potential energy we said is mgh, it still is, but instead of h we're going to use this expression that we have for that. So U is mg L minus L cosine theta. And then let's talk about the kinetic energy at the bottom. The kinetic energy at the bottom is, of course, the same as kinetic energy always is, 1/2 mv squared. But let's say I wanted to take this relationship just one step further and say, tell me what the speed of the pendulum would be as it swings through the equilibrium point. So when it swings through that equilibrium point, the kinetic energy at the bottom is equal to whatever its potential energy was at the top. So we have 1/2 mv squared equals mg L minus L cosine theta. All right, we have masses on both sides, so those can cancel out. We can multiply both sides by 2 to get rid of the 1/2, and we have v squared equals 2g L minus L cosine theta. And then, of course, the last step in that would be to take the square root. V equals square root 2g L minus L cosine theta. All right. Let's go on to the last kind of example, which is going to be our energy transfers and what happens when we deal with springs. So in this case, we have a block being pushed up against a spring with a spring constant of 400, and we're going to stretch it from its equilibrium position, and we're going to find the energy stored in that spring, and then we're going to figure out how fast it's traveling. So for this first part, it's not part of the question. It says find the energy stored in the spring. So potential energy of a spring, remember we talked in our last video, is 1/2 kx squared. So in this case, it's really just a plug and chug for that first part of the expression. 100 times 400 times 1.5 squared. And then that'll give us whatever our potential energy is. Now the kinetic energy, which we are going to deal with in a second here, 450. So this is 450 joules of energy is stored in this spring whenever it's stretched by that distance. The other question is, if the same spring is compressed by an amount of 1.5 meters from the equilibrium, what would the energy be? And the energy is going to be the same regardless of whether or not it's stretched or compressed. Part A says, how fast is the block moving as it passes through the equilibrium point? So again, all of the potential has become kinetic. So that means 450 joules equals 1/2 mv squared. And the mass is going to be the mass of our block. So we have 900 divided by 3, and then square root that. That gets you a speed of 17.3 meters per second. Okay, and then for part B, this one is a little bit different, but it says assume the block is then released from the spring and slides up a ramp set at 30 degrees. How far up the ramp will the block slide? So let's erase all of this except leave our velocity here. So it's kind of like assuming that the ramp is frictionless as well. So here we have our block, and it's traveling at 17.3 meters per second, and then it's going to come up. There's going to be a ramp here. It's 30 degrees here. The block's going to slide up the ramp. They want to know how far up the ramp does the block slide. So in this case, we have another energy transfer, but kind of in the reverse, where we have all kinetic energy at the bottom of the ramp, and that's going to be transferred into the potential energy at the top. And the kinetic energy here that it had right before it gets to the ramp is also equal to the potential energy that was in the spring. So one way we can look at it is to say that all of the potential energy that was in the spring is going to be transferred to the potential energy of the block as it goes, as it slides up the ramp. So the potential energy of our spring was 450. So 450 is going to be equal to mgh. So divide that by that. We end up with an h of 15 meters. Now, that's going to be the height of the ramp here. If we want to know how far the block makes it along the ramp, we would just have to do a small bit of trig, right? And we would have to say that 15 is going to equal the hypotenuse times sine, or the length of the ramp here times sine 30. And we get the length of the ramp to be 30 meters. That's a pretty long ramp. All right. And that is all that I have for you guys tonight. So I will see you guys with your video notes on Wednesday.